Topic 9.2.1. We have to define gravitational potential and gravitational potential energy. So we'll start with gravitational potential energy. You know that the gravitational potential energy is in the form of mgh, which means the work done to take a mass through a height h, whatever h is. mgh. But the question, the height that it travels, the height that it goes through, depends on where you take as being zero. When you take h, do you mean the height that it is from the floor, from the table, from the ground outside? Depending from your point of view, it will have different potential energies, because what are you comparing it with? So we have to take a universal point as being zero. Do we take it as the floor? Do we take it as the center of the earth? Do we take it at the top of a mountain? Do we take it at the ground outside? Do we take it sea level? The only place that can work as a universal zero point is, strangely enough, at infinity. So we basically have to measure the potential energy as taken from infinity. So, the gravitational potential energy is the work done in moving a test mass from zero, which is basically at infinity, to the point in question. So our zero reference point is infinity. So it's basically mgh is work force times distance. Now we have to do a formula for this, and we're going to basically cheat, because we're going to do force times distance. We know that the force is this force here, the distance is the distance from infinity to there, but the force is changing over that distance. We can't use this in its simplest form, so we have to cheat really and use calculus to help us. And one way of doing it is that the work done is gmm over r squared, which is the gravitational force, times by the distance it travels. And we take all these small distances, we add them up to get the complete distance that it travels, times by the force. And when we get that, you can see that this is r and this is r squared here, that one of these r's is going to cancel out. If you do this thoroughly with calculus, it works out very nicely. But what we end up with is an answer like this. The gravitational potential energy, or what we used to call mgh, is equal to minus gmm over r. This is the gravitational potential energy. Define the gravitational potential at P. First of all, we'll just go back a step and remember that the gravitational force is gmm over r squared, and the gravitational field strength, which is the force per unit mass, is equal to gmm over r squared divided by mass, which cancels with this m. So it's gm over r squared. We're going to do a similar thing to look at gravitational potential. We'll do that now. Define the gravitational potential V at point P. So this is the work done per unit mass in bringing a small point mass from infinity to a point P. It's the same as the gravitational potential energy per unit mass. So we need to have the equation for gravitational potential energy, which is minus gmm over r. But we're interested in the potential, which is the gravitational potential energy per unit mass. So we need to divide by the unit mass. So here we have the mass here and the mass here, so they cancel out. This is going to give us the potential, which is minus gm over r. Now we have a nice symmetrical set of equations here, which look at force and energy, or potential energy. The force equation is F is equal to gmm over r squared. Sorry, the gravitational potential energy is mgh, which is gmm over r. Notice that it's negative. Why is it negative? Because gravitational potential energy is always negative. At infinity, the gravitational potential energy is zero, and as it goes from infinity, it loses potential energy, so it will always be zero. The field strength is the force divided by the mass. F over m is equal to g. So that would be gm over r squared. What is the gravitational potential? This is the gravitational potential energy per unit mass. It's GPE over m, which is equal to v, which is going to be gm over r. Here again, we have a negative value. State and apply the expression for gravitational potential energy due to a point mass. So this is basically the equation. This is the formula. F V is equal to minus gm over r. What would this graph look like of V against r? Well, V is proportional to 1 over r, so we're going to get a graph which looks like this. This is the potential. This is how the potential looks as you change r, or d. It's a 1 over r relationship, but it's also negative. State and apply the formula relating gravitational field strength and gravitational potential gradient. We know that the gravitational potential is minus gm over r, and we know also that gravitational field strength is gm over r squared. Now, with V is equal to minus gm over r, if we divide both sides by a change in r, we have divided by r here, divided by r here, we end up with the change in potential divided by the change in distance will be equal to gm over r divided by r again. So this is equal to the potential gradient. How anything changes with distance is the gradient. So this is the potential gradient, and it's equal to gm over r squared, which is gm over r. The interesting thing is that you know that gm over r squared is equal to the gravitational field strength. So the potential gradient is equal to the gravitational field strength. So this is the change of potential. This is the distance over which the potential changes. And this gives us the potential gradient, which is the gravitational field strength, which is the rate at which the potential changes over distance. So the steeper the potential gradient, the greater the gravitational field strength. And we can look at it by looking at the following idea of how potential changes with distance. If we look at lines of equipotential, we can draw these lines here. A climber is going up a rock. A climber is going up a small mountain with the snow on the top. What we can do is that we can draw these lines of equal potential in the same way that you draw lines of equal height in a contour map. And this is what we're going to do. So we look at these lines. This line there and this line there are the same height. They're the same potential. So we'll draw this line of equal potential as it goes round the rock. Then we draw the next line, or the next pair of lines, for the next line of equal potential. So this one looks like this. The next two look like this. So what we've managed to do is to map what is a three-dimensional shape to show the height at different places. This is a view from above. So we can see that these lines of equal potential are highly concentrated here. They're very bunched together, which means the field strength is high. So where it's steeper, that's where it's going to be a biggest change of potential. This is going to be equivalent to a strong field. Here we have the fields of equal potential are quite far apart. So this is weaker. So in other words, here it's going to be steeper, and there it's going to be shallower. So by looking at lines of equal potential, you can see that the field strength will be high here, and it will be weak here. So this is the potential gradient, which is gm over r squared, which is equal to the gravitational field strength. So this is quite useful. It basically tells us that the gravitational field strength is equal to the gradient of the potential line. So this is the potential, how the potential changes with distance. The gradient of this line will give the gravitational field strength. Here, at infinity, the gravitational field strength will be 0. Here, it will be at a maximum. In other words, the gravitational field strength is highest at the surface of the planet. With a black hole, the gravitational field strength, it gets very, very high indeed as it goes towards the asymptote. Determine the potential due to one or more point masses. So we have the radius of the Earth is this value, the mass of the Earth is this value. Find the potential at the surface of the Earth. You know that the potential is equal to minus gm over r, so you can try this. You know g, you know the mass, you know r, so you can find the potential at the Earth's surface. But there's a little trick you can do. You know gm over r, if you multiply by r over r, you end up with gm over r squared times by r. But what is gm over r squared? You know that this is equal to the gravitational field strength, g. So v, the potential, is equal to minus g times by r. So you can do this easily enough. You don't need to put the mass of the Earth, you don't need to put the gravitational field strength, you don't need to put the gravitational constant, because you know that on the surface of the Earth this is 9.81 times by the radius gives you the gravitational potential. Describe and sketch the pattern of equipotential surfaces due to one or 2 point masses. This is what the lines of equipotential look like on the Earth. These blue lines are the field lines, which are moving downwards. The lines of equal potential, or equal height if you like, are always at 90 degrees to the field lines. Note that they're also equidistant, which means the field strength is not changing. Also, this is what's called a conservative field. If you go from this point to there, it doesn't matter which direction you go, which way you go to end up there, you will still end up with the same energy difference. You'll still end up doing the same work. This is called a conservative field. Here are the field lines, the blue lines near to the Earth, and the green lines show the lines of equipotential. Notice that they're close together near the Earth, they get further apart as you get away from the Earth. Notice also that they meet the field lines at 90 degrees, or rather they should. So remember also that dV over dr, which is the gravitational potential gradient, is equal to minus gm over r squared, which is the gravitational field strength. So a high gradient here means a high field strength. A weak gradient here means a weak field strength. And here we can show this again. The lines are very close together here, which means we get a large gravitational field strength, large gradient. Here the gradient is very small. As you get away from the planet, the field strength gets weaker, the potential gradient gets smaller, and g goes towards 0. State the relation between equipotential surfaces and gravitational field lines. Okay, we've done this. Here we can show lines of equal potential, and this corresponds to this line there, this corresponds to this corresponds to this. So as you get away from the planet, the field lines get further apart. Explain the concept of escape speed from a planet. If a bullet has enough kinetic energy, it will escape from the Earth. How fast does it need to go? If it's launched from the Earth, it needs to have enough kinetic energy to get to infinity. If it doesn't, then it will come back again. If you throw a tennis ball up, it doesn't have enough energy, it will come back to Earth. So you basically need to look at the conversion between the kinetic energy into potential energy. So when it reaches infinity, what is the gravitational potential energy? Well, we've already defined at infinity the gravitational potential energy is 0. So we need to convert all the kinetic energy into potential energy. But you know that the gravitational potential energy is also given by minus gmm over r. So basically we have to say, when does all the kinetic energy turn into gravitational potential energy? When it goes from the surface of the Earth and goes to infinity, that's when all the kinetic energy has been converted into GPA. Then it has just enough to get to infinity. So we equate these two equations here, we equate these two values here, and we end up with V is equal to the square root of 2gm over r. I'd like you to try to show that now. Derive an expression for the escape speed of an object from the surface of a planet. So you need to be able to derive this. So you end up with V is equal to 2gm over r, the square root of all that. Basically from the kinetic energy to potential energy. You should be able to do that. Then we have to solve problems with the escape velocity of the Earth. For example, if the radius of the Earth is this, the mass of the Earth is this, find the escape velocity. Remember, you can do a short trick. You know that 2gm over r, all square rooted, is equal to the escape velocity, but you know that gm over r, and if you divide by r and multiply by r here again, gm over r squared is going to be the field strength, which is 9.81. So that makes life a little bit easier for you. So remember, 2gm over r squared times by r. This is equal to g, which is 9.81. So we end up with this.